About 4.6 billion years ago, within the Orion arm of the Milky Way galaxy, a star was born. At first, it was surrounded by a cloud-like protoplanetary disk that consisted of dense gas and dust. This star was our Sun. And this is how our solar system looked before the planets emerged. The mineral grains within the protoplanetary cloud began to accumulate, forming larger and larger chunks of rocky matter, starting the process known as accretion. As the rocky chunks grew larger, they attracted more and more of the smaller matter, forming the first asteroids. Until recently, it was thought that these asteroids collided with each other, slowly growing to form planetesimals and protoplanets. The problem with this theory was that modern computer modeling indicated that, rather than leading to growth, these collisions would probably have resulted in the destruction of the asteroids. In 2019, the New Horizons probe flew by a strangely shaped object at the edge of our solar system in a region known as the Kuiper Belt. This object, named Archean, consists of two lobes connected by a thin neck. Instead of being formed by a collision, Archean's shape tells a story of two separate objects orbiting each other in synchronicity until slowly coming together and merging. This discovery points to a different hypothesis, known as gentle clumping, in which orbiting material formed into clouds that gradually collapsed into themselves. Over time, this clumping created the planetesimals and protoplanets, from which actual planets would eventually be formed. One of these planets was Earth. Many astronomers believe that after millions of years of asteroid bombardment, Earth was struck by an object about the size of Mars, in what is known as the giant impact hypothesis, or the Theia impact. This cataclysmic event generated enough heat to liquefy Earth's surface and turn it into a vast ocean of molten magma. But something else was happening that would literally change the destiny of our planet. Most of the material that was blown into space after the massive impact remained within Earth's orbit. And once again, the process of accretion began. Increasingly larger-sized chunks of material joined together and formed a new orbiting satellite, our Moon. When this new heavenly body rose above Earth's horizon, it would have been a spectacular sight. It was geologically active and almost 16 times closer to Earth than it is today. Although the giant impact hypothesis of the Moon's formation is perhaps not an obvious model, it is the most widely accepted explanation today. Let's have a look at how scientists came to this extraordinary conclusion, and why they think our heavenly companion was born from a cataclysmic event. At one point, there were three dominating theories to explain the formation of the Moon. The first one, called fission theory, was proposed by the son of the famous British naturalist Charles Darwin, George Howard Darwin, in 1878. It stated that upon formation, the molten Earth was rotating around its axis so fast that an enormous chunk of lava was ripped from its surface and started orbiting our planet as an independent satellite. The basin of the Pacific Ocean was believed to be the scar that remained after Earth gave birth to the Moon. Another explanation for our Moon's appearance is called the capture theory. It suggests that the Moon was initially an independent planetesimal that formed not far from Earth when the solar system was born. At some point, these two bodies passed at a very close distance from each other, and Earth, being a larger object, captured the Moon, shifted it from its orbit, and gradually tied it to itself. Finally, there was the third hypothesis that explained the moon's formation, called the co-formation theory. According to this model, the moon was assembled roughly at its present location out of the unused leftover rocks and dust that remained after Earth's formation. This model seemed plausible because this is how the planets of our solar system formed around the Sun. Moreover, the satellites of the gas giants like Jupiter and Saturn were born this way. But there was no way to prove or disprove any of these theories without actually getting to the moon and analyzing the soil. Our science took a giant leap forward in the second half of the 20th century with the beginning of the space exploration era. On the 21st of July, 1969, the Apollo 11 module landed the first people on the moon. They collected 21.5 kilograms of lunar material and brought it back to Earth 3 days later. Since then, almost 400 kilograms of lunar soil have been retrieved from the moon, more than enough material for scientists to analyze. But what did the analysis of the lunar samples tell us? First of all, it demonstrated that although the minerals from the moon were generally similar to those on Earth, they were quite different when studied in detail. Second, the density of the moon turned out to be much less than the density of Earth. Scientists also found out that lunar rocks are almost devoid of nitrogen, sulfur, and hydrogen, the volatile elements that evaporate first if heated. In addition, water was not found in the samples of lunar material. The moon turned out to be very dry. This meant that the surface of the moon was heated and baked at some point, purging it of all of its volatiles. Another important discovery showed that the proportion of oxygen isotopes from the moon is similar to that of earthly oxygen. This meant that the moon and Earth formed roughly at the same distance from the Sun. Being armed with this new data, scientists were able to re-evaluate the existing theories of the moon's formation and determine which model worked best. Let's take a look at the fission hypothesis proposed by George Howard Darwin. It looks convincing and explains chemical similarities between Earth and the moon, as well as the fact that the moon is always facing Earth. But this theory doesn't answer the question, where did all the volatiles go from the moon? In addition, computer modeling results reveal that a moon-sized chunk of molten lava could only have been ejected from Earth if it had been spinning incredibly fast, about 1 rotation per hour. The Earth-Moon system just doesn't have that kind of rotational inertia, so the fission theory was dismissed. The capture theory implies that the moon was formed close to Earth, and therefore should be almost identical in its chemical composition. The analysis of the lunar material showed that the moon is not identical to our planet. If the moon happens to form in a part of the protoplanetary disk far from Earth, that would explain the difference in composition. But calculations and computer modeling tell us that the moon would have passed at a very high orbital speed in relation to Earth, and Earth would not have been able to capture it. So the capture theory was no longer a contender. The co-formation theory also fails to explain the differences in the composition of Earth and the moon. If both objects had been formed from a common protoplanetary clot, they should have been chemically identical. But they are not. This theory, too, was dismissed. With none of the 3 main theories of the moon's formation being correct, scientists needed a new explanation. One that would accommodate all of the available data and resolve the contradictions of the old hypotheses. In the 1970s, a new hypothesis of the moon's formation started to take shape in the scientific community and became known as the giant impact theory. It went like this. In the early days of the solar system, 2 planets, larger Earth and smaller Theia, existed at the same distance from the Sun. We know that 2 planets cannot coexist in one orbit and will eventually collide. When this happens, the smaller planet is doomed, and the larger one survives. The inevitable collision between the two planets happened around 4.5 billion years ago, when Theia hit Earth at an acute angle. A huge amount of molten rock and heated gases were ejected into space and accumulated within Earth's orbit. And with time, the accretion process led to the formation of a new heavenly body, just over 24,000 kilometers from Earth. In essence, Theia died, giving birth to the moon we still see today. The volatiles like sulfur, nitrogen, and hydrogen escaped during tremendous heating at the time of the impact. This is why they are absent from the moon. The absence of iron on the moon is explained by the fact that almost all of Theia's iron was consumed by Earth. The moon is always facing us with one side because the moment of inertia of Earth and Theia combined in a single orbital system. It is also likely that Earth's 23.5-degree axial tilt is a result of the giant impact. Of course, we will never find absolute proof of Theia's existence, and it will forever remain hypothetical. But both computer modeling and data from the lunar soil fit with the giant impact hypothesis quite well. Meanwhile, as Earth was recovering from the tremendous impact, its surface started to cool and harden. It began to form an atmosphere of carbon dioxide, carbon monoxide, water, hydrochloric acid, sulfur, nitrogen, and methane that had been outgassed by the destruction of the mantle and the subsequent volcanoes. Although this major catastrophe was now over, Earth remained a hostile place. It was a realm of volcanic terrains, hot, dry, and barren, with a dense, high-pressure atmosphere of deadly gases. This time in Earth's history is aptly called the Hadean Eon, named after Hades, the ancient god of the underworld. It was also a time of intense geological activity, with countless volcanic eruptions. About 100 million years after the giant impact event, Earth had cooled down sufficiently for water released into the atmosphere to obtain the state of vapor, and the very first clouds began to form in the atmosphere. These water clouds increased Earth's albedo, causing more solar energy to reflect back into space and allowing the planet to cool off even further. Eventually, water was able to exist in its liquid form. Although the temperature on Earth was still above 100 degrees Celsius, the water did not evaporate because the atmospheric pressure was much higher than it is today. This allowed the water droplets to form and head down to the ground in such hot conditions. And this is how the first rain in our planet's history began. It lasted for thousands of years, gradually covering Earth's surface with water, forming the first ponds and lakes and the first seas. Until the entire planet was covered with water, turning it into an ocean world enveloped in a reddish methane mist. There was no dry land at the end of the Hadean Eon, the first chapter in our world's history 4 billion years ago. Water is essential to life. It covers 70% of Earth's surface, and it accounts for 60% of the human body. Without it, we simply would not exist. But where did this critical compound come from? For a long time, scientists have understood that even if Earth had contained water upon its formation 4.6 billion years ago, the planet was so hot that it would simply have boiled off. But we also know that there was liquid water on the surface of Earth at least 4.1 billion years ago. So how did it get here? One explanation was that once our planet had cooled off sufficiently to sustain water in liquid form, it was brought here by comets and meteorites. We know that comets consist of ice, which is frozen water. We also have evidence that our planet was bombarded by comets over the course of millions of years. Therefore, the simplest explanation seems to be that ice was delivered here by comets and meteorites, and that when it melted, it filled the ocean basins with water. So, that was the answer. Or was it? In order to verify this hypothesis, scientists endeavored to determine whether the water carried by comets was similar to the water here on Earth. What does that mean? Water is water, and H2O is a universal formula for it. So how could one form of H2O be different from another? It turns out that water is different in different parts of our solar system, and here's how. As we know, hydrogen is part of the water molecule, but sometimes hydrogen receives an additional neutron. When it does, this hydrogen atom is called heavy hydrogen, or deuterium. Our earthly water has a certain proportion of deuterium and hydrogen atoms, known as the DH ratio, which is 1.55 parts per million. As a comparison, the DH ratio of Martian water is 300 parts per million, so we know that it's different from ours. In 1986, when the Giotto probe reached Halley's Comet, scientists measured the DH ratio in its water and compared it to the water here on Earth. The two didn't match. In fact, the DH ratio of the water on Halley's Comet was twice that of ours. After analyzing the water on Halley's Comet, we started to measure the DH ratio in every additional comet we could reach, mainly remotely, using telescopes. When we examined the data from 5 more comets, not one was found to be a match. But there was still hope. Until recently, it had only been possible to measure the DH ratio in comets that came from the Oort cloud on the distant periphery of our solar system. But there is another group of comets out there, called Jupiter family comets. They reside between the Sun and Jupiter and have short orbital periods of 20 years or less. Because of their proximity to the Sun, they are exposed to significant solar radiation, and by now have lost most of their volatiles. For this reason, they're no longer very bright and are extremely hard to measure remotely. But in 2010, scientists managed to measure the DH ratio of Hartley 2, a comet belonging to the Jupiter family, and they found an exact match to the ratio of water on Earth. It seemed likely, after all, that the Jupiter family comets were responsible for bringing water to Earth. But it never hurts to double-check, so they did. In 2014, the famous Rosetta spacecraft reached the Churyumov-Gerasimenko comet from the Jupiter family and analyzed its water. This time, the DH ratio did not match, which indicated that the comets in our solar system were too diverse in their composition and probably were not the unique source of water on ancient Earth. So where did water come from? After comets proved to be poor candidates, scientists looked to the great quantity of asteroids that orbit the Sun between Mars and Jupiter and form the asteroid belt. They contain water today, and are believed to have contained even more water back when the solar system was being formed. Moreover, the DH ratio of the asteroid's water is quite close to that of our planet. The mystery seemed to have been solved once again, and articles filled the internet with headlines such as "Water brought to Earth by asteroids, not comets." This new hypothesis proposed that asteroids struck Earth, delivering a new layer of material to its surface that contained precious metals, along with carbon, and crucially, water. This layer was called the late veneer. However, recent studies have shown that some of those precious metals on Earth have different atomic signatures than the ones originating in the asteroid belt, casting doubt on the hypothesis. In addition, the timing just doesn't work. The late veneer was thought to have been delivered during the late heavy bombardment 3.8 billion years ago. But today we know that our planet was already filled with oceans at least 4.1 billion years ago. This means that the asteroids could not have been the source of our water. So what was? Apparently, its constituents have always been here, on Earth. since the start of our planet's formation. Not on the surface, obviously, but deep in the mantle, where hydrogen and oxygen elements were trapped in the minerals. When these minerals melted, the hydrogen and oxygen dissolved into the magma, forming water, which was released into the atmosphere through volcanic eruptions. When the surface of the planet was cool enough, water started forming clouds, which finally rained down onto the surface of Earth, filling up the oceans. This is the latest thinking on the subject of water's origin on our planet. Things could change in time, though, if further research leads to new discoveries. As Earth was young and extremely active geologically 4 billion years ago, volcanic cones started rising above the water's surface. They formed small volcanic islands and archipelagos, the first bits of land in the endless primordial sea. Over time, erupted lava accumulated more and more around those archipelagos, and the islands grew larger. Gradually, these small islands grew into larger land masses, the first protocontinents. It was the dawn of another geological time called the Archean Eon, which in ancient Greek means origin or beginning. Although Earth at this time resembled our modern planet more closely than during the previous Hadean Eon, this world was still a hostile and alien place. Indeed, there were familiar elements: oceans and land, winds and rainstorms, clouds and tides. But it remained a place with unbreathable atmosphere, rocky land, and anoxic oceans. As there was no oxygen, our planet did not yet have the protective ozone layer, so its surface was exposed to deadly UV radiation coming from the sun, which incidentally was 25% dimmer than today. At this time, approximately 4 billion years ago, a very important event took place. This occurrence would transform the entire planet, from its geology and atmosphere to its overall appearance, and because of it, Earth would eventually become the familiar place we know today. This event was the emergence of life. This was Earth around 4 billion years ago at the turn of 2 geological eons. The Hadean Eon, when our planet had just formed and settled, was now over, and a new Archean Eon had just begun. The atmosphere was still unbreathable for any known animal or plant, and the oceans were depleted of oxygen. As inhospitable as it seemed, our planet was already much more than just another barren rocky world in space. Quite the opposite. It was literally teeming with life, invisible to the naked eye. Primitive microorganisms inhabited its water and soil. These first denizens of life were called prokaryotes, single-celled microbes that lacked a nucleus and had no organelles. They were primitive, but by no means simple. Prokaryotes possessed all of the features that are required to fall under the definition of life. They were autonomous, completely self-sustained, and not dependent on other organisms. They were also metabolizing, or simply consuming chemicals and transforming them into energy for their bodies. Finally, prokaryotes were complex in their organization, able to evolve, develop, and most importantly, reproduce. Prokaryotes became living organisms when they obtained the mechanism that allowed them to replicate and pass on their genes. At first, such a mechanism was a single-stranded RNA molecule that was able to produce its own copies and become a self-sustained chemical system. RNA was able to store the information or blueprint of how to build a copy of an organism, as well as replicate itself according to this blueprint. The weak spot of RNA was that it was relatively unstable and easily damaged by the catalysts, or enzymes, necessary for metabolism. The solution was the emergence of a much more stable, double-stranded DNA molecule that was essentially a double RNA with a different sugar. DNA became the reliable storehouse of genetic information, while RNA became the workhorse that participated in the transcription and translation of the information into the actual production of proteins, as well as the replication process. These first microorganisms appeared and thrived in a world that would have been deadly for us or any other multicellular animal. They survived on the chemical nutrients in anoxic environments and were likely resistant to the deadly ultraviolet radiation coming from the sun, with no ozone layer in the atmosphere to block it. It is assumed that from 4.3 to 3.8 billion years ago, our planet had been regularly struck with comets and asteroids, resulting in global catastrophes. This hypothetical long-lasting disaster, called the Late Heavy Bombardment Event, was caused by orbital swings of giant gaseous planets. Some of the asteroids are believed to have been 3 or even 500 kilometers in diameter. When such large objects hit Earth, all of the water within thousands of kilometers from the impact would have been evaporated. The atmosphere would have become incredibly hot, and huge amounts of molten rock debris called ejecta would have launched into space. This would have been followed by giant tsunamis spreading away from ground zero. Shortly after the impact, ejecta would have fallen back to Earth as an intense, fiery rock shower. If the late heavy bombardment really happened, it would have been difficult for living organisms to survive. So how did life make it through such massive and frequent asteroid strikes? Firstly, the late heavy bombardment might not have been as heavy as one might think. Large asteroids probably hit our planet more often than usual, but the intervals between the catastrophes were tens of thousands or even a few million years. Life would have had time to recover. Secondly, even when a massive asteroid 500 kilometers across plummeted into Earth, only half of the planet would have been directly affected. The ocean would have boiled and evaporated on one hemisphere, but the other hemisphere would have remained a safe place for microbes. In addition, those microbes most likely populated the soil a kilometer or more beneath the surface, where they would have hardly noticed any disturbance above them. Even today, microbial underground communities comprise 70% of all bacteria and archaea that live on Earth, and their mass exceeds the mass of the entire human population by 400 times. Thirdly, recent research has shown that the late heavy bombardment might not have occurred at all. It's possible that there was only one heavy bombardment that happened during the formation of the solar system, and it ended quite early, before 4.48 billion years ago. This would have allowed life to begin even earlier than previously thought, perhaps more than 4 billion years ago. When we look at the Moon's surface, we see a great number of giant impact craters made by asteroids in the past. Some of these craters, for example the one called the Imbrium Basin, are over 1,000 kilometers in diameter, meaning that the asteroids that made them were at least 250 kilometers wide. If the Moon was intensively bombarded by large objects in the past, so must have been Earth. But when, and for how long? Was it a gradual process that started at the dawn of the solar system's formation and lasted until present? Or was it a catastrophic event when multiple asteroids hit the planets of the inner solar system at the same time? It seemed as though the analysis of the rocks from the Moon brought to Earth during the Apollo missions revealed the answer. When samples of the lunar impact melts were studied and dated, they showed that a huge impact happened between 3.8 and 4.1 billion years ago. This meant that at the same time, a large number of asteroids must have hit Earth as well. Given that it is generally assumed that by that time life on Earth had already emerged, it became hard to imagine how it managed to survive such a catastrophe. Scientists gave this event a name, the Late Heavy Bombardment, or LHB for short, because it happened relatively late in the formation process of our solar system. But why did it happen? From the beginning, the most obvious suspects to blame were the gas giants, Jupiter, Saturn, Uranus, and Neptune. There were different hypotheses as to how exactly these planets wreaked such havoc, but here is an interesting one called the Grand Tack hypothesis. Its name comes from nautical terminology, where the word tacking means the constant changing of directions of a sailboat while traveling against the wind. In this case, tacking is applied to the planets, and to Jupiter in particular. The hypothesis goes like this. When the planets of the solar system were almost completely formed, the initial collisions between the planetesimals and asteroids came to an end. The leftover debris was pushed out to the remote outer orbits, and things calmed down. But not for long. Soon, Jupiter, which initially formed at 3.5 astronomical units from the Sun, got caught up in currents of flowing gas that was still abundant at that time in the young solar system. It then started to migrate inward, towards the Sun. As Jupiter migrated, Saturn followed right behind. By the time Jupiter reached the 1.5 astronomical units point, it captured Saturn in an orbital resonance. While Jupiter made 3 circles around the Sun, Saturn made 2, affecting Jupiter with its gravity. In the meantime, the gas in between the 2 planets had expelled. As a result, both gas giants stopped their migration towards the Sun and reversed their direction of travel, starting to move away from the center of the solar system until Jupiter ended up at its current orbit of 5.2 astronomical units, and Saturn at 7. It is thought that in the beginning, Uranus was the most distant planet of the solar system, while Neptune formed between Saturn and Uranus. The gravitational disturbance caused by the dance of Jupiter and Saturn switched the orbits of Uranus and Neptune, having thrown the latter right into the peripheral ring of rocky and icy leftovers that remained after the solar system's formation. Neptune started orbiting among these rocks, throwing them in different directions, like a snowplow. This is how the multitudes of comets and asteroids from the edges of the solar system ended up heading towards the inner planets, including Earth, and eventually colliding with them. The Grand Tack hypothesis had its strengths and weaknesses in its attempt to explain the formation of the solar system as we observe it today. Until recently, it also helped to explain the late heavy bombardment event that was said to have occurred as a result of the gas giant's orbital swings. But there came another, even more plausible model of the solar system's formation that was called the early instability hypothesis. It implies that at the time the planets were just forming from the protoplanetary disk, the orbits of the planetesimals were highly unstable. The gas giants formed first, followed by the rocky inner planets. In fact, computer simulations suggest that initially there was an additional icy giant planet orbiting the Sun. While forming, the planets kept changing their orbital eccentricity, meaning that their orbits constantly went back and forth from being circular to elliptical, affecting the distribution of gas and building materials in the developing solar system. The hypothetical icy giant was thrown away into outer space, and the planets finished forming. Eventually, their orbits stabilized for good. The early instability hypothesis explains and describes the evolutionary process of the solar system in its early stages quite elegantly, and when digitally simulated, predicts the formation of a planetary system exactly like ours, with the right number of planets placed in the right locations and being the right sizes. It even allows for speculation that the hypothetical icy giant that got expelled from the solar system could indeed be that mysterious planet X astronomers are hunting for. But there is a problem. The early instability model doesn't leave any room for the late heavy bombardment event. If the solar system stabilized very early on, about 4.5 billion years ago, what caused a huge number of space rocks to hit Earth and other inner planets around 4 billion years ago? Do we even know for certain that the late heavy bombardment actually happened? We cannot find evidence of such ancient impacts on our planet. Erosion and plate tectonics would have destroyed the craters long ago. This is why scientists have looked for clues on the planets, satellites, and asteroids that are not subjected to wind, water, and constant surface recycling. Such an ideal spot was the Moon. Interestingly enough, along with the emergence of the early instability model that doesn't predict any cause for the late heavy bombardment event, the evidence that gave us reason to believe that this event did happen became less and less convincing. In recent years, some researchers have started doubting the results of the melted lunar rock dating. They suggest that dating could have given erroneous results due to the very small number of samples, or could have been affected and reset by the later asteroid impacts. It also could be that initially, scientists dated the samples that point to a single catastrophic impact that indeed did happen on the Moon 4 billion years ago, near Mare Imbrium. Moreover, in 2019, a study of the most ancient Martian meteorites suggested that all major collisions of Mars with asteroids had come to an end by 4.48 billion years ago. So where does all of this leave us? The gas giant's orbital migration and orbital instability might have taken place, but much earlier than was originally thought. Additionally, it looks as though there was only ever one heavy bombardment of Earth, during the formation of the solar system, which probably ended 4.48 billion years ago. As for the late heavy bombardment event, the evidence that has been accumulated in recent years suggests that it most likely never occurred, and early life on Earth did not have to struggle with a superheated atmosphere and evaporated water. Further research will probably clarify whether the late heavy bombardment was real or just a phantom theory. Regardless of whether or not the late heavy bombardment actually happened, large asteroids and comets did collide with Earth from time to time, leaving giant impact craters that would eventually erode away. 3.6 billion years ago, Earth was still covered with ocean and volcanic islands, but it is thought that a very small first continent called Valbara existed at that time. Today, its traces can be found in South Africa and Western Australia. Meanwhile, the microscopic inhabitants of our planet went on changing the world around them. Very early in their history, ancient prokaryotes split into major domains: bacteria and archaea. Despite their similarities in shape and appearance, members of these two groups differ from each other by their molecular and genetic characteristics. Later in the history of life, archaea would play a crucial role in the emergence of eukarya, the third major domain of organisms that include multicellular forms and contain nuclei in their cells. But bacteria were already changing our planet, creating an environment in which the existence of complex life would eventually become possible. The focus of our story, for now, is on cyanobacteria. While other organisms that populated Earth in the early Archean were using chemosynthesis, consuming chemical elements from their environments to obtain energy, cyanobacteria did something revolutionary. They started employing sunlight for this purpose in a process called photosynthesis. Thanks to cyanobacteria, life on Earth became visible to the naked eye. As early as 3.5 or even 3.8 billion years ago, these microorganisms started forming microbial mats and building layered dome-like structures known as stromatolites. They looked like piles of stones, but they were alive. The microbes populated the slimy mat layer on the top surface of the stony domes, which were usually scattered in tidal areas. When the tides were out, cyanobacteria were happily photosynthesizing above the water's surface. When the tides were in, fine sediments floating in the water were carried over the stromatolites and were trapped in sticky microbial mats. When the cover of sediment which accumulated on the dome became thick enough to block the sunlight, the microbes moved upwards, producing one fine layer after another. If we slice a stromatolite vertically, we discover fine layers of sediment representing its growth, much like the rings of a tree. This process was repeated again and again, cementing multiple layers on top of each other, forming continuously growing domes or columns. Stromatolites could grow several meters high, forming the first reefs long before the time of corals. They also took part in the continent building process, adding more and more bacteria-formed minerals. At about 3.1 billion years ago, the only significant landmass on Earth was the ancient continent Ur, surrounded by a seemingly endless ocean. Although larger than its predecessor Valbara, was a fairly small continent. It consisted of parts of modern Antarctica, Australia, India, and Madagascar, and its name means original or primitive in German. Cyanobacteria, with their mats and domes, were the only visible life on Earth for billions of years. Stromatolites populated large tidal areas around the continental shores, taking various forms, shapes, and sizes. Cyanobacteria were not only responsible for making stromatolites. These microorganisms played a much larger role in the history of our planet. They dramatically changed Earth's atmosphere by pumping oxygen into it. But there is a little twist to this story. The cyanobacteria were photosynthesizing or utilizing sunlight to obtain energy. And as we know, the byproduct of photosynthesis is oxygen that is released into the environment. Theoretically, our atmosphere should have contained oxygen since the appearance of cyanobacteria, at least 3.5 billion years ago. But geological evidence indicates that there was no significant, or in fact any, amount of free oxygen in the water or air until around 2.5 billion years ago. But why? One possible explanation is that although cyanobacteria did photosynthesize, instead of releasing oxygen, they were oxidizing iron. Unlike today, Archean oceans were green because of the great amounts of greenish ferrous iron dissolved in them. It's possible that ancient cyanobacteria, or their ancestors, instead of releasing pure oxygen, were binding it with ferrous iron and oxidizing it, or, to put it simply, making it rusty. This oxidized iron was not dissolvable in water as it used to be in its previous ferrous state, and was continuously falling to the ocean floor, accumulating in layers. During the daytime, when cyanobacteria were actively photosynthesizing, iron particles were falling to the bottom. During the night, no iron was released. Indeed, all over the world, geologists find vast formations where layers of iron oxides alternate with shales and cherts that were accumulated during the Archean times from about 3.5 to 2.5 billion years ago. These layered iron deposits are called banded iron formations, or BIFs. Today, banded iron formations are the major source for mining iron ore, which is used to produce steel. It's incredible to think that everything made of steel, from kitchen appliances to the cars we drive, is a byproduct of photosynthesizing ancient bacteria that lived and produced iron oxide billions of years ago. In the late Archean Eon, 2.5 billion years ago, banded iron formations were deposited less intensively, and free oxygen started to accumulate in the water and the atmosphere. 2.4 billion years ago, the levels of oxygen on Earth started to rise so fast, in geological terms, that scientists called this process the Great Oxidation or Oxygenation event. But why did cyanobacteria stop producing iron and start releasing oxygen? The answer is quite simple. All the greenish ferrous iron dissolved in the oceans had been used up. When there was nothing remaining to oxidize, photosynthesizing organisms were left with no other option but to release free oxygen into the environment as the byproduct. As the Great Oxidation event progressed from 2.4 to 2 billion years ago, the world started to look more like it does today. The planet began forming a protective ozone layer in its atmosphere that blocked the sun's ultraviolet radiation, which was deadly for any form of complex life. The oceans turned from greenish to blue as they lost all of their ferrous iron. For the first time, the sky was deprived of its otherworldly reddish hues and also became blue. Only the moon would have seemed strange because it looked enormous, as it was still much closer to Earth than it is today. The geography of our planet also changed by the late Archean Eon. Ancient was replaced by a significantly larger landmass assembly called the Land supercontinent that stretched from north to south and included parts from most modern continents. Land existed from 2.7 until 2.4 billion years ago, when the continents broke apart and continued their tectonic dance. But what would happen after such a dramatic change in the planet's atmospheric composition and the appearance of a large landmass? It would be the dawning of a new eon. shivering winds, and frozen wastelands. A white silence stretches from horizon to horizon. This is our planet 2.4 billion years ago, at the very beginning of the Proterozoic Eon. The world entered a state of global glaciation when even the equatorial regions were covered in ice. This global freezing event, known as the Huronian glaciation, lasted until 2.1 billion years ago and is believed to have been triggered by a chain of successive factors. As we already know, by 2.4 billion years ago, photosynthesizing cyanobacteria had enriched our planet's atmosphere with oxygen, causing the Great Oxidation Event. Although this enrichment ultimately created an environment that could sustain complex life, it came at a price. It likely caused the planet's first mass extinction. To most of the microorganisms that populated Earth at that time, oxygen was a poisonous gas. But an even more dramatic consequence of this event was that oxygen replaced greenhouse gases in the atmosphere. The amount of carbon dioxide, which is known for keeping our planet warm, dropped dramatically. And methane, an even more powerful greenhouse gas which had dominated our atmosphere since the Hadean Eon, was reduced to the trace levels we see today. One reason why the concentration of CO2 dropped was the formation of the first large supercontinent, Knorrland. When this large landmass became exposed to the air, CO2, which was dissolved in rain droplets, fell to the rocky ground and became trapped in the sediments, being withdrawn from the atmosphere. With much less greenhouse gas to trap the heat, the global climate became cooler, and ice sheets started to build in the polar regions and the highlands. As the ice grew, the albedo effect kicked in. White glaciers and snow-covered areas reflected the sunlight back to space, preventing the atmosphere from accumulating heat, thus cooling it even further. It didn't take long for the enormous glaciers to build up and advance from the north and south to meet at the equator. This was not the first time that glaciers had appeared on Earth. In fact, 2.9 billion years ago, there was an ice age known as the Pongola glaciation, but it was nothing like as severe as the Huronian event. Now, for the first time, the whole planet became icebound and entered a state known as the Snowball Earth, and apparently, life was at least one of the factors responsible for it. It was a time of several long ice ages, when glaciers advanced and retreated for 300 million years, with the longest ice age lasting for 100 million years. But how did life survive this freezing catastrophe? Although Earth was mostly frozen, there were some ice-free areas. They formed near geothermal vents and fields that would melt the ice around them, just like we see in Iceland and Antarctica today. Such places would have been perfect for life to survive, and even thrive. Some microorganisms could have lived in subglacial lakes like they do today in Antarctica's Lake Vostok. Others could have lived in air bubbles that were frozen in the ice. Finally, they could have occupied cryoconite holes that melted in ice under the accumulation of mineral dust and volcanic ash. Such holes are present in many modern-day glaciers. Earth remained frozen until 2.1 billion years ago, when it suddenly broke through its icy trap. But what made it possible for our planet to escape its snowball state? The first answer is volcanoes. During the entire time of glaciation, they pumped greenhouse gases into the atmosphere until there was a sufficient amount to keep the planet warm again. The second answer would be our fortunate position at the optimal distance from the Sun. If Earth had been located marginally farther out, it would probably have remained frozen until today, being not much different from cold, dry Mars. 2.2 billion years ago, Earth entered an unusual time known as the Loma-Gundy excursion, when oxygen in the oceans and atmosphere was in abundance, but there were no organisms to consume or breathe it. Things probably remained like this for around 200 million years until the first organisms capable of efficient use of oxygen arrived. These organisms were the eukaryotes. In contrast to the simple internal structure of already existing prokaryotes, with their genes freely swimming in cytoplasm inside of the cell walls, eukaryotes had their DNA neatly packed inside the nucleus in the center of the cell. Moreover, they possessed very important organelles called mitochondria that were responsible for breathing oxygen and producing energy. While early eukaryotes were still single-celled organisms, they were 10 times larger than prokaryotic cells. It is believed that the earliest eukaryotes existed at least 1.9 billion years ago, while the first known eukaryotic fossils come from 1.8 billion-year-old rocks. These oldest eukaryotes belong to a diverse group of mysterious microfossils, collectively called akratogs, which in Greek means unknown origin. Today, scientists believe that they were the first single-celled eukaryotic algae, or the first phytoplankton of the Proterozoic oceans. Although akratogs were minute organisms, no larger than 0.15 millimeters across, they were giants in comparison to prokaryotic life forms. Some of these eukaryotic akratogs, like Dictyosphera, were round with smooth surfaces, while others, like Shayiosphaeridium, were covered with tiny spines or processes. There is even a 1.6 billion-year-old spiny akratog called Tapania, whose morphology suggests that it might be related to fungi. At least 1.87 billion years ago, but possibly even 200 million years earlier, a peculiar organism called Gripania spiralis appears in the fossil record. Unlike anything else that lived at this time in the oceans, thin, tube-shaped Gripania reached several centimeters in length, and therefore could be seen with the naked eye. It lived in water and was likely attached with one end to the bottom sediments. Scientists are still not certain what Gripania was. While some suggest it was a colony or string of prokaryotic cyanobacteria, others consider it to be an early, true eukaryotic alga. This mysterious organism survived and remained virtually unchanged for another 1.2 billion years, almost until the end of the Proterozoic Eon. While scientists remain puzzled by Gripania, there is another enigmatic organism that seems to be completely out of place on the timescale. Meet Discagma buttoni, an extremely problematic 2.2 billion-year-old fossil from South Africa. It was small, from 0.3 to 1.8 millimeters in size, and shaped like a tiny urn with an opening at the top. But the most fascinating thing about Discagma was that it lived on land. Its tiny fossils were connected into bunches by threads on the surface of ancient soil, strikingly resembling modern fungi. The problem is, it appears in the fossil record much earlier than any known eukaryotic organism. Therefore, Discagma must have been something simpler than plant, animal, or fungus. Perhaps it was a prokaryotic organism. If not, the emergence of eukaryotes would have to be pushed back at least 300 million years. Nevertheless, somewhere during the first half of the Proterozoic Eon, the earliest eukaryotes appeared, marking the beginning of multicellular life as we know it, giving rise to 3 new biological kingdoms: plants, fungi, and animals, which are all forms of eukaryotes. If we were to look at our planet from space 1.8 billion years ago, we would see the land masses combined into a supercontinent called Columbia, or Nuna. It existed from 1.82 to 1.35 billion years ago, until it broke apart, as every supercontinent eventually did. The land most likely looked reddish, like the Martian surface, but on Earth it was surrounded by blue oceans and topped with a layer of white, curly clouds. As oxygen became widespread in the atmosphere, the soil started to corrode. The weathering process activated by oxygen started to destroy granites and basalts that contained iron, turning them into rusty red soil. Between 1.8 billion to 800 million years ago, life on Earth was stagnating. No complex organisms appeared, and no cataclysms or drastic climate changes occurred. The history of Earth was decidedly dull and uneventful for a full billion years. Scientists call this period the Boring Billion. But what was the cause of this continuous and tedious stability? And did nothing interesting actually happen for such a long stretch of time? Indeed, life was already capable of oxygenic photosynthesis. Oxygen-producing cyanobacteria were in place, but for some reason, the atmosphere and oceans did not contain enough oxygen to sustain any complex life forms. Something was keeping the oxygen levels too low. At this time, oxygen-releasing life forms coexisted and competed with sulfur-using organisms, green and purple sulfur bacteria and methanogens, archaea that produced methane. Neither of the latter organisms produced oxygen. The oceans during the boring billion were stratified. There was a thin 3 to 6 meter deep surface layer that was oxygenated and inhabited by photosynthesizing single-celled green algae, including acritarchs. Below this clean layer and down to the bottom, the waters were completely anoxic and populated with purple sulfur microbes and methanogens. Towards the end of the boring billion, when oxygen-producing organisms finally outnumbered sulfur-using bacteria, as well as methane-generating archaea, oxygen levels started to increase, paving the way for the emergence of complex life forms. By 1 billion years ago, a red alga called Bangiomorpha discovered in the Canadian Arctic appears in the fossil record. Despite its antiquity, it strikingly resembles Bangia, a genus of red alga that exists today. Fascinatingly, Bangiomorpha, which inhabited the shallow seafloor just a little more than 1 billion years ago, had male and female spores, making it the first known sexually reproducing organism. In 2020, Chinese scientists discovered a peculiar fossilized green seaweed called Proterozoic anticus that came from 1 billion-year-old rocks. It was only 2 millimeters in size, but of enormous importance. It may be the oldest fossilized green plant ever found. As we have just seen, the boring billion was a time when a number of important changes took place, and probably wasn't that dull after all. When it officially ended 800 million years ago, the land masses assembled into another supercontinent called Rodinia, which derives from the Russian verb to give birth, and was surrounded by the ocean Mirovia, from the Russian word mir, which means world. The land was still devoid of any complex life. Only bacterial mats surrounded the water bodies and wet areas, but in the ocean, things were quite different. While bacterial mats like soft and colorful carpets covered the bottom between mounds and pillars of stromatolites, the water column was populated with microscopic organisms, and substantial areas of the seafloor were covered with kelp-like seaweeds. It's likely that the first animals or metazoans appeared at this time, in the form of single-celled protists called choanoflagellates. These organisms look like little sacs with a collar around a thread-like appendage called a flagellum. As the flagellum beats, it pulls water through the collar, where all of the food particles are collected. Choanoflagellates are known to form colonies, where newborn cells don't float apart, but stay together with the others. In cooperation, they use their flagella to create a powerful filtering system. At some point, different cells started performing different functions. Some were responsible for feeding, while others formed the outer protective layer, and this is how true metazoans emerged. Sponges are believed to be the very first animals to appear on Earth. Indeed, the earliest animal fossils belong to a sponge-like organism discovered in Namibia that existed 760 million years ago. It was named Otavia antiqua. Ranging from 0.5 millimeter to 5 millimeters in size, Otavia fed on algae and bacteria, sucking them through their tiny pores into a central body cavity where the food was processed. These animals likely formed colonies that sat on the seafloor between algae, filtering water for food. Around 720 million years ago, Earth started to cool down again. In fact, there were at least 2 subsequent glaciations, and quite possibly, our planet turned into a giant snowball once again. These glaciations are thought to have been caused by similar factors that caused the Huronian event: the increase of oxygen in the atmosphere and chemical weathering as the Rodinia supercontinent started to split apart. Both processes removed CO2 from the atmosphere, making it cooler. This ice age lasted for 85 million years until 635 million years ago, and the whole time period was named the Cryogenium. Once again, volcanoes eventually replenished the atmosphere with CO2 and thawed the global ice cover, returning the climate to normal. And Earth has never since experienced such severe glaciations as seen in Proterozoic times. Around 620 million years ago, the majority of land masses gathered together in the southern hemisphere and formed another supercontinent called Pannotia. Its assemblage coincided with another ice age called the Gasquier's glaciation, but it lasted only 340,000 years and was not nearly as severe as the previous ones. It appears that at that time, Earth just managed to escape another snowball state. The final 94 million years of the Proterozoic Eon are named the Ediacaran period, and this is when truly strange and almost alien creatures appeared. Around 570 million years ago, in what is now Newfoundland, Canada, 1 kilometer below the water surface on the dark sea floor, we encounter the first large, complex multicellular organisms. Spindle-shaped bodies of Fractophusus that reached up to 40 centimeters lay on the soft microbial mats, connected to their young with stolon-like filaments. Cabbage-like Bradgatia reached about 20 centimeters and was attached to the bottom with a bulbous holdfast in the center of several leaf-like petals. Fronds of Charnia masoni that looked like large feathers bending back and forth in the water currents reached up to 60 centimeters, while 2-meter-tall Trapacia towered over this deep water garden. All of these organisms are collectively called rangeomorphs and are distinguished by their unusual structure that is unknown in anything that lives today. Their bodies branched into fractal modules of 4 subsequently smaller orders. Each module was composed of a series of smaller modules that looked exactly like the full creature. Scientists are having difficulty determining what these organisms actually were. Lichens? Animals? Fungi? Giant single-celled creatures? Or were they a completely different form of life that vanished long ago, one that deserves to be put into a separate, now extinct kingdom? While the debate is still on, we know for certain that rangeomorphs were not plants, although superficially they looked like them. Plants require sunlight to perform photosynthesis, but these organisms lived far too deep down in the water for light to reach them. Another question is how and on what did these creatures feed? The common thinking is that they were practicing osmotrophic feeding, a passive absorption of dissolved organic carbon from the water. This is probably why the rangeomorphs grew fractally, increasing their surface area to absorb as many nutrients as possible. Later, around 560 million years ago, we still encounter rangeomorphs like Charnia and 6-lobed reindeer. But along with them, new types of strange organisms start to appear in the fossil record. They looked like pancakes that were lying on the top of microbial mats, most likely feeding on them. This group of Ediacaran biota has been named the Proarticulates and is mostly known from ancient shallow marine environments of northwestern Russia and southern Australia. 2 of the most well-known proarticulates are the 25-centimeter-long Yorgia and its larger 1-meter-long relative Dickinsonia. These creatures consisted of 2 rows of tubes or isomers that radiated to the sides from the central axis of the organism. The most confounding part about these creatures is that they lack mouths and guts, as well as any external sensory or reproductive organs. Scientists also think that proarticulates were able to move around on the sea bottom in search of new food sources. For example, when Dickinsonia had absorbed the entire microbial mat beneath its body, it moved to another location to keep feeding. Indeed, there are traces of fossils of Dickinsonia and Yorgia that show multiple imprints of the same organism, hinting to its mobility. Additionally, a recent study of lipid biomarkers extracted from Dickinsonia fossils revealed something fascinating: cholesterol. This indicates that they might have been animals after all. While the affinity of Dickinsonia and its kin is still debated, there was another Ediacaran creature called Kimberella, whose classification is more or less agreed upon. Trace fossils suggest that it was mobile, bilaterally symmetrical, and might have possessed a feeding organ with teeth similar to that of mollusks. This is why Kimberella is thought to be a bilaterian animal, possibly an early mollusk that grazed upon microbial mats, as modern snails do. But the most convincing discovery, indicating that the first organisms resembling modern animals appeared in Ediacaran times, before the Cambrian explosion, was made in 2020. Through most of the second part of the Ediacaran period, there is fossil evidence of burrows that with time gradually increased in complexity, and were most certainly made by worm-like animals. But the makers of these burrows had remained elusive. Finally, rocks from South Australia revealed 555-million-year-old fossils of a tiny worm-like animal that was named Eukaryotes. It lived and made its burrows among other Ediacaran organisms of uncertain origins. But Eukarya was something far more familiar. While this several millimeter-long organism was neither impressive nor pretty, it's hard to overestimate its significance. Scientists believe that animals like Eukarya arrived just before the time when life radiated into a huge variety of fauna, such as worms, mollusks, arthropods, and even vertebrates. Earth's long 4 billion-year journey was a prerequisite for life to achieve today's wonderful diversity. After the Proterozoic Eon was over, life literally burst into various forms and shapes. During the next 540 million years, in what is called the Phanerozoic Eon, life inhabited all possible ecological environments. From vast oceans to land, and even the air, changing this ancient planet into the place we call home.